So what we're going to talk about today is a small part of what is a very long story. It spans about 30 years if you want to go from beginning to end. It has more facets, twists, and turns than you can possibly imagine. It's probably the wildest science story you're ever going to hear about. And I'm just going to try to cut a certain arc through the story in order to keep it within an hour. So there's parts I'm going to be able to tell you, parts I'll just give little hints about, little teasers about, but I won't have a chance to tell you about. If you have a chance to hear another version of this talk sometime, you'll probably hear different aspects of the story emphasized. So in particular, I mentioned that for those of you that are coming from Penn, I know I'm supposed to go there to give a talk next month. That'll emphasize different components that I'm going to talk about today. So in particular, when Bob invited me to give this talk, I said, well, the problem with the subject is that it has no connection to the subject of this workshop, which is topology. He said, well, never mind, go ahead and talk about it anyway. But as I began to prepare the talk, I realized, oh, actually, there's a very obvious connection, which there is actually a topological issue which is at heart here, which is part of the motivation for this search for natural quasicrystals. So I thought that would be a natural way to begin the story, the arc in the search for a natural quasicrystal. In fact, although that part of the story in large part dates from a few decades ago, there are still some open issues there that remain unresolved. And then what I'll try to do is I'll try to hop skip in a rapid way to a part of the story which is completely different in character, just to give you a sense of the wildness of character of this subject. You might call it the adventure part of the story. It involves caviar, Kalashnikovs, the Koryak Mountains, and Kamchatka. So this and more. And before we're done, maybe we'll even have a chance to go get one more hop further, even off the planet. So that's the story I'm going to try to tell you today. So first of all, let me begin where at least the beginning so far as most physicists and mathematicians are concerned when the idea of quasicrystals first emerged was, first came to public attention was in 1984 when Dan Schachmann, Ilan Blech, Denis Gratius, and John Kahn announced the discovery of this material, this dendritic phase you're seeing of aluminum 6-manganese, which you can see has a apparent, approximate pentagonal structure to it. But the important thing is that when you actually look at it under an electron microscope, it diffracts electrons like a crystal, but with a symmetry that's strictly forbidden for crystals. So when they said that, what they meant was this was the diffraction pattern they obtained. It contains rather sharp spots, which remind you of the Bragg peaks, the truly perfectly sharp spots that one might get for a perfect crystal. On the other hand, if you look at the symmetry of this pattern, for example, if you look at those bright spots in that ring, you find that they form a decagon corresponding to a 5-fold or 10-fold symmetry. And those are symmetries which are famously forbidden for crystals. And more than that, when you rotate this sample off angle from this axis of symmetry, you discover it has many 5-fold symmetry axes arranged along the symmetry axes of an icosahedron. And an icosahedron is the most famous ultra-forbidden symmetry for crystals because it breaks the laws of crystallography 6 times over, rather. Six independent 5-fold symmetry axes. So there it was. Now, as it turned out, there was a theoretical explanation waiting in the wings, quite independently of the work by Schachmann et al. My student, Dov Levine, and I have been working at the University of Pennsylvania on a hypothetical phase of matter that we had dubbed quasicrystals. The idea was they were supposed to be like crystals, but with a slight twist. And the main twist was that instead of being periodic, they're quasi-periodic, which means that instead of the atomic arrangement being described by a single periodic function, it's described by a sum of periodic functions where the ratio of the periods is irrational. For example, 2 periodic functions. Now, the interesting thing is that the moment that you relax the condition from periodic to quasi-periodic, although you have a well-ordered system, although it's perfectly well-defined, it's perfectly predictable, the laws about rotational symmetry are totally broken. So whereas for crystals, you're restricted to being, periodic systems, are restricted to one of 32 point groups or 230 space groups. The quasicrystals, there's no restriction. So all the symmetries that you thought were forbidden are now allowed. And in principle, if you could make solids of those forms, all the symmetries that you thought were forbidden are now should be possible for solids as well. Now, if you think about these quasi-periodic systems in real space, you could think of them as having an almost translational symmetry. By that I mean, because they're quasi-periodic, I can make translates of a lattice relative to the original, such that when I overlay them, they'll almost overlap. For a crystal, they'd perfectly overlap, but they'd almost overlap except for a finite density of differences. I can make that density of differences get smaller by simply making a bigger and bigger translate. So I can make the differences, the density of differences, as small as I like, just by making bigger and bigger translations, although there's always some finite density. So it's an almost translational symmetry in real space. There's also an almost rotational symmetry in real space. It's not true that there's a point at which I can rotate it and it exactly overlaps itself, but it will overlap itself up to a finite density. And if you allow me to choose a different point in the lattice, I can make that density smaller and ever smaller, as small as any bound that you would like, but always some finite density. So in real space, it's kind of a subtle difference from periodic in going from exact to almost symmetries. In reciprocal space, the story is much simpler to describe. The density is described just as for crystals as a Fourier sum over wave vectors g, which lie in a reciprocal lattice. And the diffraction pattern is truly Bragg peak, just like for a crystal. Just like for crystals, the reciprocal lattice can be written as an integer linear combination of basis vectors e sub I. The key difference is that for crystals, the number of basis vectors is d in d dimensions, whereas for a quasicrystal, it's greater than d. So for five-fold symmetry, for the icosahedral symmetry, for example, the number of basis vectors is 6, even though the structure lives in 3 dimensions. As a result of that, when you look at the reciprocal lattice, because the number of basis vectors is greater than the number of space dimensions, what you find is along any given direction, the Bragg peaks, the diffraction spots, the G's, okay, lie at integer combinations of 2 incommensurate length scales. And when you take all integer combinations, what that means is between any 2 Bragg peaks, you'll find yet more Bragg peaks. So whereas a crystal will form a lattice in which there's a minimum separation between Bragg peaks, in a quasicrystal, if you have a high enough resolution, you look between any 2 peaks, you'll find yet more peaks.
The number of vectors that you allow always finite? I mean, there's a notion of quasi-periodic and almost periodic in mathematics.
Yes. So finite.
Are you insisting that the frequency come out of a linear set which is dependent, so it's more vectors than the space dimension, but still finite?
Exactly. Yes. Yes. So we're not considering continuum property. So one could imagine. So that would take us to yet another class of possibilities.
And that number, that excess number of vectors can be any number?
Yeah, it's set by the symmetry. So the minimum is set by the symmetry. So for example, for icosahedral symmetry, those 6 bases, you'd have 6 basis vectors, and they'd point to along the 5 symmetry axes of an icosahedron. If you want 147-fold symmetry in 2 dimensions, you can guess it's going to take 147 basis vectors. And that will determine, all the incommensurate length scales. That symmetry will determine the incommensurate length scales that you get. Now, the inspiration from this idea was the study of this pattern, which is the Penrose pattern. Penrose had invented it 10 years earlier as an attempt to try to make a pattern which is forced to be non-periodic, a set pair of tiles with rules with which you can put them together that forces them to be non-periodic. But what turns out to be the case is that it's much more special than that. It's really a quasicrystal. It's quasi-periodic. That may not be obvious by looking at it, so we can do these various tests, the translates in real space and the like, or we can simply do the Fourier test, look at the reciprocal space. So let's look at the reciprocal space. So this is the one where I want to turn off the lights. And can you get the ones in the front? So basically what I've done is I've taken this pattern, or a larger version of this pattern. And let's see, I'm not sure it would be better to go this way or this way. And I've reduced it on a slide, and it's going to act like a diffraction grating. Let's see how we do. Let's see if I can, what's the best way to do it? Okay, there you can see. So there's the diffraction pattern of it, and I hope you can see that, despite my shaking hand, that it has a 10-fold symmetry. And you can kind of begin to perceive the fact there's spots and there's more spots and there's more spots. That's a characteristic pattern of a quasicrystal diffraction pattern. It's immediately recognizable because of its Bragg peak structure and because of this incommensurability along any direction. So as an immediate, it's not hard to recognize one when you've got one.
What's inside that?
Oh, so this is just a slide, which is, if you were to look at it and I were to blow up in a slide projector, would just be a Penrose pattern. It's just that pattern. I just shrunk it enough that I could get a diffraction pattern that is good enough for the purpose. Yeah. And the rest is just a laser, using a laser.
And how big are those compared with the wavelength of the laser?
I'll leave that as you an exercise. You saw the size, you saw the distance. It's no different than a First Quasicrystal. It's the same story as a, well, actually there is a scaling issue there. Yeah, I'll leave it for you as an exercise. It's not obvious because the structure is self-similar. That means that the pattern repeats itself in ever smaller scales. But I'll just show it for you one more time. If you really look closely at that pattern, the very innermost part of it, although it's hard for your eye to perceive it, at some point the spots are getting fuzzed out, and that's telling you something about the length scale. Okay. Okay. Now, to see in real space that it's quasi-periodic, it's one way of doing it, which I find useful, is to, and that's the way we first realized it, Dove and I realized it, was to put these little line segments to etch every fat tile with the line segments on top, every skinny tile with the line segments on the bottom. Then the Penrose's matching rule in this case, it isn't the way he expressed it, but Penrose matching rule in this case reduces to the statement that I'm only allowed to put two tiles together if the line segments line up. And if you do that, you get this pattern. And if looking at this pattern, you weren't sure what you were looking at, is it ordered, is it disordered, what have you got? When you look at this pattern, it's absolutely clear that what you've got is something which is very well ordered. If at the moment I put a little tile on with a line segment along this way, it's obviously forcing a whole line of tiles, things to arrange along this line. So it has some kind of order to it. It's also clearly not periodic. What is it? Well, you'll find there's 5 sets of lines, each of them oriented along one of the edges of a pentagon. So that's telling, and they're all the same. Each set is the same. So that's already telling you that you've got something which is 5-fold symmetric. And then if you look at the patterns along any lines along any one direction, you find there's they only occur in long and short spacings, where the ratio of longs to short lengths is the golden ratio. And if you follow the patterns of longs and shorts, long, short, long, etc., what you find is that it's not periodic, but in fact it's a Fibonacci sequence in which the ratio of the number of longs to the number of shorts is a ratio of subsequent Fibonacci numbers, which means in the infinite limit it approaches an irrational ratio, which means it can't be crystalline. Crystalline would have to lock into some rational ratio. But more than that, a Fibonacci sequence is expressible as a sum of periodic functions, where the ratio is the golden ratio. So it's quasi-periodic. It's much more. It's not random either. It's much more special than that. And once you know that secret, well, that sort of cracks the problem for you. Now you can begin. Once you know it's quasi-periodic, there's various ways of generating the pattern. For example, one way of generating the pattern is as a projection. A quasi-periodic function could always be viewed as a projection or cut through a higher dimensional periodic function. So this is just a discrete example of that. You can get this pattern by cutting in a certain way through a 5-dimensional hypercubic lattice, for example. A certain cut will give you this. And once you know that, you realize, well, why did I restrict myself to 5-fold symmetry? Why didn't I choose 7? Why didn't I choose 11? Why didn't I choose 17? Okay, there's no limit. It's obvious you can pick up any symmetry you want by this same procedure, and that includes the case of icosahedral symmetry in 3 dimensions. Now, just producing the structure is one thing. If you want to imagine atoms arranging themselves in that structure, you might ask for more. For example, it turns out for certain symmetries, like the Penrose example, you can find rules which constrain the way these can fit together, such that the only way they will fill space without holes is if they make that structure. So we call those rules matching rules, and those are more special. We know them for certain symmetries, we don't know them for other symmetries. We don't know if it's because they don't exist or we just haven't figured them out yet. But the cases where two cases where they're well known is the Penrose. That was what Penrose accomplished. That was what he accomplished, and we know how to generalize that for 3 dimensions with icosahedral symmetry. Now, there are various ways of realizing the tiles in 2 and 3 dimensions. I showed you the rhombuses. Penrose has another pair of tile shapes called kites and darts. There's many isomorphic ones. Similarly, in 3 dimensions, a common set which is used is 2 rhombohedral shapes, a fat and a skinny, but you have to make 2 versions of each. So there's really 4 fundamental units in the set. An alternative is the set I'm going to present here, which is, involves 4 units. And there's the rhombic triicontohedron, the rhombic icosahedron, the rhombic dodecahedron in yellow, and then just a plain old rhombohedron. And what you can see from this picture, and you'll see when I pass these around, is there's kind of Lego-like joinings which constrain the way in which they can go together. They can go together in some ways, but not others. I'll just give that to you. And you're welcome to pull those apart and put them together again, as you wish. And let me now turn on these lights again. And so the point about those rules is that they have the property that I can fill space following those rules, and the only way I can fill space following those rules is to form a 3-dimensional icosahedral pattern. So here I built a certain piece of it to give you a sense of what the structure would look like as you build it out. I got to give myself a little physical space here. Okay. And so I've kind of done it in layers. So here's a layer that would come off. That's one layer that would come off. Then here's another layer would come off. So if I'm going along a symmetry direction, I could divide it into layers. And if you look at any one layer that you're seeing here, if you stare at them a bit, you'll come to realize eventually actually cores can be cut through with planes, 6 different planes that cut through the 6 different directions. An analogy to what we were seeing in 2 dimensions for the Penrose with the 5 sets of lines. So there's planes instead of lines that cut through this structure, and these rules are enforcing the fact that the planes go continuously through. So these are kind of delicate. You're welcome to come up and look at them, but I don't want to pass these guys around. The last time I did that in Princeton, the first person I handed it to was John Conway, promptly dropped them. They spread all over the floor, and we spent about half an hour cleaning them up. So don't want to do that again. Okay, yeah.
So in this case, the one set of planes is parallel to the planes that's cut off.
No, actually, they're all kind of skew. Well, you can kind of see there's one that's coming through here. You can kind of almost see, if you stare at it a while at the right angle, you can kind of catch it. Yeah, there is one that's kind of cutting right there. Right. Yeah, and cutting through there, right. And then there's the 5 others, which are, if you look down from above, you can kind of see them crisscrossing. They don't have exactly the same phase relation as Penrose. This is a subtly different. Getting to these structures rather than Penrose is not trivial. They do share the property that there's the planes like the lines. They are self-similar. They can be subdivided into similar shapes like Penrose. And they have these Fibonacci rules. So they share the properties of Penrose, but actually there's quite a bit of subtle difference between the two that had to be worked out before we could get this pattern. Okay. Now, if you calculate the diffraction pattern of this along a 5-fold symmetry axis, which is along there, let's say imagining putting point scatterers at each of the vertices, this is the diffraction pattern you get, where here, these are true Bragg diffraction peaks, but the brightness represents the relative intensity. The radius represents the relative intensity, but you should think of them as being Bragg peaks, and where we've cut off the intensity at some threshold, otherwise you'd fill this whole pattern. So it's very similar to what you saw for the 5-fold along there. And then this is what Shechtman had gotten. So the comparison between those is what led to the suggestion that maybe what Shechtman has is a quasicrystal. And of course, I think as people know, he won the Nobel Prize in chemistry this last fall for discovering this material. But in point of fact, the idea that this is a quasicrystal was not immediately accepted. There was considerable reason for skepticism. A lot of the articles that you read about now talk about Linus Pauling as being one of the chief skeptics. Pauling thought it was some sort of multiply twinned crystal. That idea never really held much sway. If it hadn't been Pauling, you would never have heard that idea. The data didn't really support that idea. But there was an alternative problem, which there was an issue, a serious issue with aluminum-6 manganese, which is that it doesn't really have truly sharp peaks. They look rather sharp to your eye in that picture, but when you really measure them in X-ray diffraction, they actually have a finite width. And that opens the door to alternative models. And a simple alternative model, in fact, one that Shechtman himself, I think, still talks about and still thinks is correct, at least for his material, is the idea of what's called an icosahedral glass, where you imagine there's icosahedral units which are packed randomly, but in such a way that they join edge to edge and they have common orientation. So that ends up producing a pattern of peaks, which, if you look carefully, there would actually be diffuse scattering. That would be hard to detect, but it produces a rather sharp pattern that is not easily differentiated from Shechtman's data. At the same time that this was being realized and this icosahedral glass was coming out, another criticism of the quasicrystal model emerged, which is that it seems to require some kind of non-local interactions in order to grow. So I've told you that it's ordered, but if you think about it, if it's quasi-periodic, one of the properties of something that's quasi-periodic is that no two positions are exactly the same. If you follow their environments arbitrarily far out, they eventually must differ to some degree. And so if atoms are going to form in a pattern which never exactly repeats, how are they going to figure out to do that without knowing where the atoms are everywhere in the system without some sort of long-range interactions? And the kind of materials in which this was found, like aluminum 6 manganese, this phenomenon was found, we don't think have such mysterious long-range interactions. What about the Penrose rules? Don't those give you a solution to this? Well, no. Penrose's rules tell you there exists a solution, but it doesn't tell you that it's easy to find. So it's a little bit like just an ordinary jigsaw puzzle. They give you the picture, you know the solution exists, no one promises you that it's easy to find. It might take lots of trial and error. So if I give you a pile of Penrose tiles and ask you to build the tiling, the chances are you will have the experience that after just a handful of tiles or 2 handfuls of tiles, you'll begin to make errors, like in this case. So then you'll have to take stuff back and put it back in, and this will just repeat itself ad nauseum. So it looks like you'll have a high density of errors in it, which means, and so the argument went, you're not going to get a very perfect quasicrystal. You're only going to get highly defective things, which means it's some sort of hypothetical idea, but nothing that you'll ever reach in the laboratory or in nature.
Excuse me.
Yeah.
So what you're starting with the internal reflection lines.
So the reflection lines just think of as being a matching rule which tell me when I'm allowed to match and when I'm not allowed to match. So just think of them as edge matching, as rules as to when I'm along an edge I'm allowed to match and not. I'm not allowed to look across the system to see where I match.
But when you found the ones that you showed us with the first slide,
yes.
You did it by experimenting?
No. So there you produced the pattern first. I mean, there you did a global construction which enforced the pattern. Is that what you mean?
Well,
yeah. In other words, in this case, what I've done is I actually was on a computer, laid down a tile randomly. I chose fat, then I did this one, this is actually showing the order which I added them, and by putting them in, by doing them sequentially, the way atoms might add to a crystallite, I ended up in trouble. Okay. Whereas in the other case, what on the other hand is that Penrose showed is that following those rules, I could, in principle, given enough time, tile as much as I like. Then I can go. Then those lines wouldn't match up. But to get them to match up, it appears as if I need long-range information. Like I need to look across to see. So, for example, so when I added this 5 tile over here, you see it has a line segment there. It perfectly matches up with this tile over here. No problem there. But if I looked across, I would have seen there's a problem, going to be a problem downstream. But I needed long-range information in order to do that.
But you have a theoretical way of predicting how to draw those lines.
Yes. Yeah. Well, yeah. That's prescribed. Yeah. Yeah. There's a precise relationship between the lines and the tiles that take you from one to the other. Now, just to is this non-local idea really needed? Well, one way of examining that question is to consider the question for the case of the Fibonacci sequence. Okay, so suppose, we'll just try to build this problem in one dimension. Suppose I want to build a quasi-periodic sequence, specifically a Fibonacci sequence, a chain of links, long and short links. So I give you a pile of longs, I give you a pile of shorts, and I say build a Fibonacci sequence. Of course, one way I could do that is just calculate globally what a Fibonacci sequence is, write out the whole thing, and then just put them along there. But then I'm using a global map. I'm using long-range information to answer the question. So what I'm insisting that you do is actually develop a set of rules which only look back, given a chain of a certain finite length, only look back a finite length and then make a decision as to what to do. Develop those set of rules. Now you're allowed to use the ideal Fibonacci as a guide to learn the rules, but once you've learned the rules, it ought to be self-sustaining on itself. Can we find such a set of rules? So for example, suppose I had gotten long, short, long, short, and I'm trying to decide what to do next. Well, if I look at the ideal pattern, I notice that shorts are always bounded on either side by long. So this is not a hard problem. What to add next? I obviously add a long, and that only requires local information about this end of the chain. So I didn't need to use any long-range information to answer that question. Yeah, so the idea is, can I find I don't mind if it's a finite depth, but I want it to be finite, and then we might disagree as to whether we like finite or how, we're satisfied or not. But unfortunately, the problem is going to be worse than that. The problem is I'm going to need infinite depth. And it begins to be illustrated by this problem, where I'm trying to decide here at this point whether if this long to add a long, or to add a short, and of course if I add a short, I'm going to add a long again, because short's always followed by long. So I go back to this point over here. I say, do I want long, long, or long, short, long? And I look at the ideal pattern. I say, here's long, long, and here's long, short, long. So they're both equally good. I can't make a decision based on that information alone. I have to go one back. So then I look at one back, and I go short, long, long, short, long, short, long, and you'll find that in the sequence above. And go another one back, and you'll find that in the sequence above, et cetera, et cetera, et cetera, until I get to this end of the chain. And then I'll discover trouble. Because when I go all the way back to this end of the chain, I see what I've really got here now is long, short, long, short, long, long, short, long, short, long. And if I make this choice, I'm going to get long, short, long, short, long again. I'm going to repeat the sequence 3 times, and that's not allowed. OK. So I needed to go back at least this far. But unfortunately, this is a self-similar structure. So I could also choose a chain which is arbitrarily long and run into the same trouble again. So this is a proof that in one dimension, I absolutely cannot do this. I need infinite range information in order to make the right decision as to what to do on the far end. And now, you think back at the Penrose problem, and you remember the Penrose problem, we have 5 Fibonacci lattices going at the same time, so it sounds like it's impossible to have anything with a local rule. The only problem is, that's wrong. The 5 actually makes a difference. The fact that they crisscross actually makes a difference. Conceptually, if you think about it a bit, it's because sometimes when you get stuck in one direction, you might get unstuck in another direction. And that might be enough to get you going onwards. And also, it's because the problem is a little bit more can be more subtle than, as you think about it, there's subtleties to the issue when you're trying to mimic something that might be in a physical system. So it turns out that the first step to going beyond, to finding local rules, you can find local rules that make some physical sense. And the first step is to relax your, is to change from thinking about matching tiles along edges to think about adding tiles to a vertex. So think about a vertex rule rather than an edge rule. So then I can divide, so it turns out in the Penrose tiling there's 7 allowed vertices, only 7 kinds of vertices that can occur. And so given some cluster of tiles, on the edge I'll have some open vertex, and I can classify that edge, that vertex rather, as either forced or unforced. Forced if there's only one choice consistent with the 7 possibilities. Unforced if there's 2 or more. Okay? And so now my local rule is simply add at forced sites only. So what this means is that if you think about it as atoms joining to a, that are impinging on some growing crystallite or something like that, quasicrystallite, that the forced sites should be viewed as very sticky and the unforced sites as non-sticky. So if you only stick at forced sites, then you won't make an error. Now, here's an example where now I'm switching from the lines. I'm going to use the Penrose arrow rules. They're equivalent. So this is more closer. This is actually what Penrose had introduced for his matching rules, not those little line segments, but he had introduced for the skinny side tiles. Oh, gee, I think it goes this way. Single and double arrows, such that you're only allowed to match tiles along an edge if the arrow direction and arrow type is the same. Doubles against doubles, singles against singles, and arrow direction against arrow direction. Those are equivalent to those line segments I was showing you before. So that's what you're seeing in the middle here, and you're seeing kind of half arrows along the edge there. And here's a cluster, and this cluster happens to have the property that it has a forced site on the forced vertex on the corners. And so I'll move this tile in here. It doesn't fit that way because I have single against double arrows, but if I rotate around, there it goes. It will fit hopefully in there. Okay, so I've had a forced site there. Now, that's not the only force site. If I continue this, I'll find more and more force sites. And what this program does is it keeps adding force sites until you run out. So we'll add. And what happens is now we've run out. We've reached what we call a dead surface, a surface which has no force sites left. If I were to choose add a tile randomly at this point, that would immediately create new force sites, and they would propagate yet new force sites, but it would only grow out a certain distance. And I could repeat this, each time going out from one dead surface to the next, and it would grow out ever farther. Sometimes it grows a lot, sometimes it grows a little. But it has to go in this herky-jerky way, which is in a sense non-local in the sense that to decide, the first rule said just only add at 4 sites. That's local. It only requires a local decision. But to decide that I'm at a dead surface and run out of 4 sites, that's a non-local decision. So in a sense, I violated what I was trying to do. But there's an interesting way out. And it involves a topological issue, which is the one I wanted to get to, which I'm going to begin instead with a different cluster, core cluster, which is going to be this one. And this one is not a proper piece of perfect Penrose tiling. I cannot fill in the inside of this consistent with the Penrose rules. Okay? It's an example of a defect that was, it was first pointed out in a very different context by John Conway, and he called it a decapod. And so it's a structure, this donut thing can be filled outwards with Penrose tiling, but cannot be filled inwards in it. So it would be a kind of point defect to it. Now to see its topological property, it's useful to think about these arrow rules I just showed on here. So suppose I take a circuit, any circuit through a Penrose tiling. I'll begin with just a single tiling, which runs along the edges. Okay? And I'll make a rule that every time I'm not going to care for this, about the difference between single and double arrows. Every time, if I'm running along this way, if I'm running around the circuit this way, every time the arrow's in my direction, I'll add 1. And every time I run against it, it'll be -1. Okay? So it's a topological property of the tile. And obviously, when I do this, the sum will be 0. And for this one, the sum will be 0. And so it's not hard to see that if I have a piece of perfect tiling and do the circuit through any long closed circuit of edges, it has to be 0 because it's just a sum of zeros from the individual tiles. Okay? But if you look at this one on the inside, these are all single arrows running the same way. So the integral around this circuit is 10. So we might call it charge 10 decapod. You can also make ones which are charge 8, charge 6, charge 4, charge 2, as well as, in addition to, perfect Penrose tiling, which is charge 0. Okay? So now, and the same would be true if I went along the outer edges. Of course, it's a topological property that lasts everywhere. Now, the interesting thing here is, in this case, when I now make the rule that I again add to 4 sites only until I get to some dead surface, here's what happens. It runs off to infinity.
Does it always run off to infinity in all directions?
Yeah. Yeah.
It might not run in some direction, but that was...
No, it actually runs off to 0 infinity in all directions. Well, essentially because it never runs out of 4 sites. There's nothing to... when you watch these things grow, what you find is that there's... four sites tend to run in strips around certain parts of the outer edge of the tiling, and then they reproduce new 4 sites elsewhere. It runs out to infinity and completely fills space. So what that means is that this is a topological defect which has the nice property that with a simple local sticking probability rule, you can actually force things out to infinity just like for any crystal. Now that said, there's something mysterious about this which is not yet understood. Okay? This is a topological defect which has some kind of long-range influence on this system. It obviously has a long-range field associated with it, but we don't understand what it is. For example, topological defects like dislocations and disclinations have both a discrete interpretation and they have a continuum limit. This should have a continuum limit, but we don't understand what it is. We also don't understand what the analog would be for other symmetries. I can guess some simple ones, but in general, whether it exists for other symmetries in 2 and 3 dimensions. So there's definitely some interesting open issues here. But the important thing is that in principle, okay, there's nothing to prevent you from growing something which is perfect, which, as it turned out, not that I've been able to find anything useful. Okay, so we do know that dislocations do correspond, and that quasicrystal correspond to a dislocation, can be viewed as a dislocation in a higher dimensional hypercubic lattice and projected in a certain cut into let's say 2 dimensions. But we don't know that for the decapod. Decapod it's some mysterious thing which is peculiarly quasi-periodic and has no analog. Now, as it turned out, just around that time, partly due to the influence of these ideas and partly just because by luck, sure enough, one began to find examples of truly perfect quasicrystals that, so far as we know, have, to the extent to which one can measure in the laboratory, have much sharper peaks than Schechtmanns and really have Bragg peaks. And this is really what I would call the first clear quasicrystal. You can see it has these beautiful facets and its peaks are resolution limited, as fine as any you get in any quasicrystal. It happens to be a mixture of aluminum, copper, and iron. Since that time, over 100 other materials have been found which are similar quality. So it's not unique to it's not unique to just one chemical system. And there are even examples where one can literally trace in atomic level imaging, Penrose tiles on top of the tiling. So it looks, for all intents and purposes, as if we really have one of these ordered systems, just as described here. That said, again, because the subject has always been there's always been this sort of skeptical side to the subject. There's still been skepticism in the face of all this debate that somehow this idea is too complicated that nature could never figure out to do it. And so there is a competing idea that says that, in fact, all quasicrystals are somehow entropic rather than energetic. These ideas are suggesting that you could imagine, in principle, the tiling rules are saying in principle, you could have a system whose atomic interactions could, in principle, force it to be a ground state. The tiling is kind of a discrete analog of such a possibility. It shows it's possible in principle. But another point of view is it says that somehow nature never is going to do that. It's always going to choose something which it can be entropic, but if you were to grow it, unless you were to grow under very pristine, careful conditions, the way these guys are done, you'd never expect to see a very perfect quasicrystal, or a quasicrystal at all for that matter. It would tend to crystallize. And under carefully controlled conditions, just the right composition, just the right temperature, pressure competition. So the question is, how delicate are things? And this is really what underlies the story that I'm talking about today, which is the search for natural quasicrystals. Because here's these 2 ideas. My own view has been, based on the things I've been showing you, that there's nothing that tells me that a quasicrystal can't be as stable and shouldn't be on the same footing as a crystal. And if so, how do we know that we made the first quasicrystal? Maybe nature beat us to the punch. On the other hand, if they're very, very delicate and can only be grown under where you can take full advantage of the entropic advantages in certain circumstances, then you would not expect them to be found in nature, because nature gives things pretty, you wouldn't expect to find them in nature. That was for me a chief motivation for this search. And of course, if you were to find one in nature, that would be very interesting, because it would open up a whole new field in mineralogy and geology, because up to this point, the only known minerals have all been ones with crystal symmetry. So there's that possibility. And if you were to find one that had been missed, that might suggest that there are geological processes that we don't yet understand. So there are a number of reasons why you might start this venture. Now, how do you start such a search, though? Well, in a sense, it started informally. Shortly after we introduced the idea of quasicrystals back in the 1980s, just traveling to museums and looking around and see if someone misidentified something was sort of method 1. Didn't yield anything. But about a dozen years ago, I began a systematic search and the first part of that search was developed with Ken DeFay at the Department of Geosciences, a bright undergraduate by the name of Peter Liu, who's now a postdoc at Harvard, and Nan Yao, who's director of our Imaging Analysis Center at PRISM on campus. So the idea was to, first of all, began on the theoretical side, to do a computer database search through diffraction patterns for quasicrystals. Now, if you had diffraction patterns like this, you wouldn't need a team of people to do this. Any one of us could do it in a matter of moments or hours. But you don't have large catalogs of diffraction patterns like this, because this requires a high quality sample, single grain under ideal circumstances. And for most materials, natural or unnatural, we don't usually often have that kind of quality. But what there does exist is a catalog of what are called powder diffraction patterns, where you take an X-ray diffraction pattern from a powder of many crystallites which are randomly oriented. And what that does is it turns this pattern and essentially spins it around the center, so it turns into that pattern. So, in fact, all the information is just one-dimensional now. It's compressed into wave vector versus an intensity. And so you get a spectrum of peaks or rings that you would cross as you go outward from the center, and that's called a powder pattern. And there exist computer databases. There exists an international an international catalog, computer database, which contains something like 80,000 different powder diffraction patterns, 9,000 of which are natural, the rest of which are synthetic. And so if you could manage to identify a quasicrystal from this information, you could, or at least a likely one, that would be the way to conduct the search. That was the concept. And in fact, it would work if you really had perfect information, if the information in the catalog were perfect, because although you've lost a lot of information, you've lost all the symmetry information here, if this were really a quasicrystal, there are certain relations, incommensurate relationships between the sizes of those rings, and that you should be able to read off. And those were the kind of metrics we tried to develop. We developed a set of metrics that would help us, out of this 90,000, separate the things that were nearly quasicrystal or good quasicrystal candidates from the rest. And it worked pretty well. We ended up with something like 50 materials, of which 30 or so were natural minerals, which clustered around what you might expect for a quasicrystal by these metrics, and the rest of them were far away in parameter space. So it did pretty well. The next part of the search was you have to actually go around search in museums and collections to find those materials. They're not easily gettable, the natural ones. So there's lots of stories there. At the end of which of a few years we failed. We failed to find anything that worked. All the likely things we found up to that point, we didn't find all of them, but all the ones we found, well, what turned out in the end was that when we actually went to measure the diffraction pattern more carefully, we found it wasn't well measured the first time. The catalog was an error. And if you put in the correct values, it returned from being close to quasicrystalline to back in the crowd of everybody else. So our catalog was a problem. But nevertheless, we wrote a paper explaining our methods and saying we still hadn't found them all. If anyone wants to help join the search, please let us know. We'd be happy to work with you. So 6 years later, this fellow, Luca Bindi, answered the call. He's the head of the division of mineralogy at the Museo di Storia Naturale at the Università di Firenze, which is a good mineral museum, but nothing special. Okay? But it turns out it was quite special that he's the one that answered the call, and among the many remarkable twists and the turns in the story is that of all the people, he answered the call. Number one, because of what he had in his museum, as it turns out, and number two, because he happens to be a very interesting, fanatical person, just as fanatical about this subject as I am. The subject requires a lot of fanaticism to pursue. I won't tell you all, you're not going to hear about all the twists and turns, but believe me, there were many times when we were in a hopeless situation, and more than once he's the one that kind of dug us out of that hopeless situation by some sort of breakthrough or discovery. So it was really marvelous luck that he was the one that answered the call. The first year was spent hopelessly looking through things in our list that were in his museum and discovering one after another that they didn't come out right. And then he made a good suggestion, which was, why don't we look at the things that aren't in the catalog? He had some things in his museum that weren't in the catalog at all. Why not look at those? And then we began to look at them. We looked first at one that chemically was closest to known quasicrystals. So a lot of the known quasicrystals, for historic reasons, have aluminum in them. So he looked at this sample, which turns out to have an aluminum alloy in it, a metallic aluminum alloy in it. So it was labeled Khatirkite. It says on the box it comes from Khatirka. Khatirka is the name of a river in far eastern Russia. Koryak refers to the Koryak Mountains in that region of the Khatirka River. And depending upon where you're sitting, let me just point out that What you see in the box is mostly clay, plastic. The rock, it's just there to hold the rock in place. The rock or pebble or grain, whatever you want to call it, is that thing on the tip. It's only a few millimeters in size. But if you blow up to other big size, it looks like a big boulder. And it's a rock. It's not a mineral. It's not a pure substance. It has lots of stuff going on in there. It has many common elements, common minerals, most common elements you find on the outside, like spinel and olivine and pyroxene and things like that. And then the darker material, that's our copper aluminum material. And just like in everything else that we did, all these experiments are destructive to the samples. You slice and dice the material into thin sections so you can do the first set of experiments, and this is an example of one of those slices. This is just showing a place where there's essentially only metal phases. And then you go through this tedious process of sort of chemically probing. Every one of these spots here corresponds to a chemical electron microprobe where you're measuring the local chemistry. And so what you observe is there's 4 different phases inside here. The yellow one corresponds to the Quasicrystal that was labeled on the box. And if you look up Quasicrystal in the International Mineral Catalog, it's a crystal, a known crystal, copper, aluminum 2. There's a red phase, and that turns out to be cupellite, again in the International Mineral Catalog, again a known crystal, copper, aluminum. And then there were 2 phases, the green, some mixture of aluminum, copper, iron, and the blue, some mixture of aluminum, copper, iron, and those were not classifiable in the International Mineral Catalog, so those were obvious targets to go for. To go for them means you now take this thin sample and you try to punch out one of those tiny little things and see if you can capture enough of them that you can do an X-ray powder diffraction pattern. And that's what he did. And he sent them to me. The green one came out clearly bad, and the blue one came out, yeah, as good as the best ones we had found up to date. So worth looking at more closely. So the sample made its way to Princeton. We're in our PRISM laboratory. Although I'm normally a theorist, one of the joys of this subject is that I get to be experimentalist in part of this subject. So we had some fun getting this thing off of, getting these grains apart. Some of these grains were thin enough that we could do diffraction pattern on them. And when we did that diffraction pattern on them, which was an interesting morning, the first thing we found was a pattern on top. Just a gorgeous, gorgeous quasicrystal diffraction pattern. It's overexposed, so you can't realize how gorgeous it is. This is much, much better than Sheckman's pattern. Much more perfect. As perfect as anything that we make in the laboratory. And then when you rotate the samples at off angles, you could eventually find the axis. An icosahedron has 2 full symmetry axes and 3 full symmetry axes. You got the whole thing. But again, much more perfect than the original samples. You know, the degree of perfection that really requires a strict control in the laboratory. But look, I'm sorry, and then we did the composition. So we measured the composition of it, and it turned out to be this composition, which, if you have a good memory, you've seen before. It's the same as that one. It happens to match up exactly to within the limits as the first so-called high-quality quasicrystal formed in the laboratory. In fact, this is a material that had been very much studied at Penn when I was there. And I had a sample of it. I still have a sample of it on my desk. And we could actually compare, therefore do a differential comparison of its composition to this one. You couldn't really resolve the difference. So it was as good as really the best sample we had, but it was not made under anything like pristine conditions. It's there in the middle of this rock, and there's all this complex stuff going on here. Somehow, something has managed to make this under conditions that we would never, ever have thought to do in the laboratory. Wouldn't even know how to do in the laboratory. So we could share that we found a quasicrystal, but we also had immediately a mystery, which is how did this form? How did nature manage to do this? So that began sort of the second stage of the story, which has lasted several years. How did nature manage to do this? The first people we consulted with were Lincoln Hollister, who's in our Department of Geosciences here, a well-known petrologist who works on lots of terrestrial and lunar materials. And soon after, he introduced me to Glenn McPherson, who works on meteorites, and told him the same story I told you just now. And they both had the same reaction, which is very interesting, but unfortunately, what you've got there is impossible. And what you've got there is a piece of slag. Slag is a 4-letter word for human waste product, industrial waste product, from an aluminum foundry or something like that. And I explained to them, no, 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 we know quasicrystals exist, and we've made them in the laboratory. And they said, no, no, no. The quasicrystal part of the story doesn't bother us. What bothers us is that you're telling us that there's aluminum metal in your material. And aluminum has a voracious appetite for oxygen, strong affinity for oxygen, more than almost any other element. So we don't find aluminum metal in nature. We work really hard to remove the oxygen from aluminum. There is no natural aluminum. It's only way, so that's why we think it comes from downtown Berlin and not somewhere off in the middle of the Koryaks or something like that. So that was discouraging, and probably if I were a geologist, I would have stopped at that point. But and if Luca were not fanatical, he probably would have stopped at that point. But I think neither of us were completely satisfied with the answer, because there were some things about the material I haven't told you about which made us suspicious of this idea. Plus, even if this were right, I still wanted to understand how it was done by accident, because normally in the laboratory we have to work really hard to accomplish the same thing. So at this point, the investigation broke into two parts. One part which is really a detective story, which is how did the sample come to be in this Florence museum? Did it really come from the Koryak Mountains where the box said it did or not? And if you're naive like me, you would come up with the assumption, sure, if the museum says it did, it surely did. I know now so many cases of fakery in this business that no, the chances were about 50% that that was right. And the second thing is more of a scientific investigation. Could we, from the little grains we had left, not just the metal, but other things we see, somehow prove the loan that the thing did not, it was not slag, or it was slag, one way or the other. So I had to become an expert on slag. Spent a year becoming an expert on all the different ways we use aluminum and different kinds of byproducts we produced. It's interesting, and helpful because, well, let me talk about I will not talk about the detective part of the story, although that is part of one of the most fun parts of the story. And just to give you an impression of the parts that you are missing, what was involved in this detective story included things like secret diaries, super plumes, smuggling, secret Russian lunar samples, gold prospecting, there were KGB agents and death threats, lightning, fakes and fakers, Cuban Missile Crisis. All this, believe it or not, has something to do with this story. And I'm not going to tell you that. But in the end, to jump that, we did find, after about a year and a half, through all kinds of circuitous means, all that and more, we actually did find the guy, the person who actually picked that rock out of the ground for the first time, back in 1979. This is actually a picture from 1989, and this isn't the same spot, but it's representative. That's what it looked like 10 years later, and it's rough. It's it's basically the same thing. Gives you the sense of the scene. His name is Valery Kryachko. He's not an academic. He works in a sort of the mining industries, broadly defined, in Russia. And he was completely surprised that the rock that he had found in 1979 turned out to be of any interest at all. He explained to us how he had been sent to this river in far eastern Russia, the Listventovia stream, which was a gold panning area, to look for platinum. He was sent by the Institute of Platinum to look for platinum. He spent several days there sifting through clay, and you'll see an example of that clay shortly, and failed to find any platinum. He did find some odd little pebbles and grains, and he brought them back to the head of the Institute of Platinum, and that's the last he heard of them since 1979, until we contacted him in 2010 and told him that actually they were much more interesting than platinum. And then he got very excited, because by this point the announcement that we had found quasicrystals in a rock that was purportedly from Russia had been announced, that had come out in Science, and it had gotten a certain amount of play in Russia because it was a Russian sample. So he had heard that story and had no idea that he was connected to it. So he was very enthusiastic and eager to provide whatever help we wanted, and that turns out to be crucial to the story. In particular, he pointed out for the first time exactly where on a map this material was found. So here's where we're talking about, where this pincushion is. This is Alaska. This is far eastern Russia. Wasilla is somewhere like here. So if you go out Some people describe, people often, when I talk about this as Siberia. Let me point out that you're much more exotic than that. Siberia ends here. You are beyond Siberia. This is all the Kamchatka Peninsula. It's divided into this lower portion, which is the part most people are familiar with. It's the part that has volcanoes. Tourists can go there. Then there's this other part, which is desolate, which has a population density which is about 1/100th of Western Sahara. And most people cannot go there. It requires special permissions to go there. It's historically a defense zone for obvious reasons. And even Russians, although they can travel here freely, they can't travel there freely. You need special permissions to go there. And here in the middle of the Koryak Mountains, which are right around here, in the middle of nowhere is where our guy was. So now we know, at least from this, that there's no aluminum foundry there, that's for sure. There's no aluminum foundry within thousands of kilometers of there. It's not even, the closest town is here, and that's several hundred kilometers away. And civilization, as you know what it's kind of like over there someplace. Or in Wasilla. Okay. So meanwhile, can we prove from the rock alone that this is not slag? Well, again, I'm not going to take you through all the twists and turns of the story. The story always has been laying itself out, even up to today, when there was even today some surprises. It's always been laying itself out in this interesting way where you get information bit by bit. But let me just jump to what was the critical piece of evidence, which was this photo shown here and things like it. So I love this photo because on first sight it looks like it's nothing, just like an abstract or something like that. But it's really, really very, very interesting. It's something very, very unlikely surrounding something impossible or thought to be impossible. So the stuff you're seeing around it is silicon dioxide, the same stuff that makes up quartz or sand. Nothing more common than that. Okay, except that it has the wrong diffraction pattern. So it turns out it's not quartz and sand, but it's a polymorph of silicon dioxide, which only forms at ultra-high pressures, around 10,000 gigapascals or higher. So something that would form deep under the Earth, like near the core mantle boundary, or it's been known to form in space where you have high-energy collisions between meteorites, or when meteorites hit the Earth, it's called stishovite, and it's a polymorph which is only observed under these extreme conditions. You're never going to find it in an aluminum foundry or in any kind of normal process. So that immediately tells you that this grain, which is found in the middle of the rock, is not made in a foundry. And as for this one on the inside, that turns out to be quasicrystal. So it's impossible in the sense that the quasicrystal was not supposed to form at all, but more than that, here it's sitting right next to silicon dioxide. That's oxygenated. This is not. There it is. This picture alone captures all in one shot everything you need to know. Ultra-high pressure, somehow you have something, aluminum metal sitting next to something that's not. Okay? And if we can crack that puzzle, we'll have cracked the whole thing. Now, the first step is you want to know is, did it form in inner space or outer space? Did it come from deep under the ground, and was it kicked up in some kind of superplume event, as some would suggest? Or did it come from outer space? And it turns out the way to do that is to measure oxygen isotopes. So again, I'm skipping actually over this part of the story, but it turns out by measuring the abundance of oxygen isotopes, rare isotopes compared to normal oxygen, you can distinguish terrestrial from non-terrestrial. And you can even distinguish among the non-terrestrial things, is this something that came from Mars? Is this something that came from a moon of the moon? Did it something that came from a moon of Mars, etc.? Okay, and it turns out that our guy comes from outer space. It's an extraterrestrial, but it's much more interesting than that. It's a very, very ancient extraterrestrial. So when we started this investigation, my goal was to see if we could get something older than the quasicrystal seen by Shechtman, or probably seen in the last century. So up till now, the oldest quasicrystal that we knew of was made in the last century by humans. Okay? But now we know that the oldest quasicrystal was made actually in the very beginning of the solar system. It turns out that our sample, the oxygen signature of our sample strongly indicates that it's not just from a meteorite, but a very, very special subclass of meteorites, which we think formed at the very beginning of the solar system. So 4.5 billion years ago. Older than the Earth, or contemporary with the Earth, as old as the Earth, or if not older. And therefore, one of the first minerals to have formed in the solar system. So among the thousands of minerals we know, most of them formed after the Earth became oxygenated, after the life formed on Earth at the 3.5 billion year mark. If you go back to the beginning of the solar system, before there were planets, so far as we know, we only know of something like 200 different minerals that existed then. Most of them in microscopic forms you'd hardly count. So what you're looking at when you see this sample now is actually one of the first minerals to have formed, one of the top 200 to have formed in the solar system. So it went from one of the newest to one of the oldest things made by humans, made by nature. So quite a dramatic change, if true. Now, I didn't tell you this part of the story, but it turned out one of the ideas we'd been pursuing all along was the idea that this might be a meteorite. That was always on our list. But what we've been told by the meteorite experts, including Glenn McPherson, who I had mentioned before, is that there are many reasons why this couldn't be so. Not just the aluminum, but there are many, many features of this rock, 4 or 5 of them, that completely were against the rules that we knew about all known meteorites. So what this did was turn the whole subject on its head, because now we know it is a meteorite, but we don't understand, it doesn't fit into the usual meteorite story. So now we want to know a lot more about it. But we only have a few grains left, and we've used up everything we've got. So the only way you can ever learn more about it is to think about going back for more. And I just explained to you that you can't go back for more for lots and lots of reasons. Among other them, it's a restricted region, and number 2, you got to know where to go, where to look. But that said, last summer, July 22nd, here we are on the edge of the tundra, about to head off. In our group are 5 Americans, 1 Italian, 7 Russians, and a cat, heading off in these strange vehicles. We managed to pull it together. Again, I'm skipping the story of how we managed to pull it together. A big part of it had to do with Valery himself. We couldn't do this at all unless Valery were willing to go and were enough health to go. And so fortunately, he was in all those things. And he not only was willing, he's the only person that knew where he found the rock in the first place. But more than that, he actually helped organize all the ground game logistics in Chukotka, because he still had friends that lived in that area. He doesn't live there anymore. He never lived there, but he doesn't live there. He lives in Voronezh in the west. But he was crucial. The other crucial component was getting the Russian Academy of Sciences involved. Marita Yadovskovia and Vadim Disler came along with us as well. We brought along, we had these 2 drivers, Bogdan and Victor. Bogdan looks like he can lift a tree and literally lifted trees to help us. And Victor had his own skill set. Victor was actually trained as a geologist, but now works in Chukotka as a driver. He likes that job better. His wife came along as cook, although she also is trained as a geologist. Everyone here had sort of double and multiple lives. After geology, she turned to law, and she was crucial to helping us get a lot of the local permissions. You needed military, federal, FSB, local Chukotka, lots and lots of permissions in order to give this thing a go. Plus, you turned out to be an excellent cook. And then they carried along Victor and Olya carried along their cat. Luca, who normally does not work in the field, he's a laboratory crystallographer type mineralogist, but he came along. He was critical because he actually knew what to look for and has these marvelous eyes that can pick out of a pile of dirt something which is interesting. And he was just remarkably reliable at that. Glenn McPherson, who had been one of our strongest skeptics, meteorite expert, came along. Of course, now he knew that it was a meteorite, and so that's why he was very interested. Chris Andronikis, who is a geologist from Cornell, is a structural geologist. And so we were interested not just in looking for this stuff, but to see if we could have any chance of finding it, but also studying the whole structural geology of the area to see if for some reason maybe we're wrong. Maybe it's not meteoritic. Maybe it's something to do with the local geology. And so that's what he was brought along for. And he happens to also be a bear expert. He works at National Grizzly Bear Park very often, and so he knew about bears. Alex Kostin, who's a Russian who came as a translator, but also was helpful for many, many reasons. We brought along 2 graduate students. Some of you may know Mike Eddy because he was a graduate student at Princeton, but he's now at MIT. The other graduate student is someone who I've known literally since he was a baby. So that's my son, Will. who's now a graduate student in geoscience at Harvard. These were our trucks, which were some sort of cross between, I don't know, tanks and snowcats. Here you're seeing them on so-called flat tundra. There's really no such thing as flat tundra. I mean, if you were to walk across this stuff, it's actually hard to walk across even when it's flat. You can't go very far in it. And the whole ride there is like a roller coaster ride. And just to give you some impression of it, this is a typical experience in crossing a stream. We've got to cross many, many streams. You learn to hate streams. I mean, from the outside, it actually doesn't look so bad. From the inside, it feels like you're falling off the end of the earth. Then the next scene, you're going to see, I'm going to show you, is a scene where we're going along, and Victor suddenly turns left. Normally, we've been traveling on roads, and I'm saying, I don't see any road. And his response, all I see is this forest of trees, and he gives me a look which I think amounts to saying, who needs roads? So although the trucks may seem invulnerable from this picture, I should warn you that they actually were very vulnerable. We had all kinds of problems with them. The motor had to be put together several times. Here was the most dangerous crossing the Katirka itself. You know, because this is all tundra and permafrost, you don't know how deep any river is when you're going to cross it. It changes from season to season. So we weren't quite sure if it was too deep for us. And further, it wasn't clear whether or not we floated or not. These were supposed to float, but then there were arguments about whether we weighed down too much to float, and did we float? All I know is we made it there and back. We did manage to make it. There were billions of mosquitoes, very unpleasant. There were really bears. When we went, Chris Andronicus gave us bear lessons. What do you do if you run into a bear? The answer is you die. But you can do a couple of things before that happens, to try to discourage them. But he told us that if we see 2 or 3 bears, are very shy. By the time you see them, you've had it. But and they're pretty fast. But he told us if we saw 2 or 3 of them, we should be really concerned. We're in intense bear country. And we saw 20 bears on this trip. And fortunately, none of them at very close range. But there were bear tracks right around our camp, you know, huge bear ones. And so we did have to watch for that. There were also some unusual treats, like, you know, Victor and Bogdan would fish salmon out of the stream and make caviar. So we had caviar with mosquitoes for breakfast. There were Kalashnikov lessons. Here's us where we were camped was about a mile or so from the stream. So these are all areas which could contain bears. But the idea was if you stayed in groups of 3 or so, they weren't supposed to bother you. So far as I know, that's true, but I don't want to test that experiment too often. Here was the stream. Of course, you get to the stream, it's been, what, since 1979, since Valeri's been there. Is he going to find the spot? Well, it wasn't so obvious for the first few hours because a lot of things had changed, as you might imagine. But we actually did find the spot. So this is in the background. You can see there's kind of this clay bed there behind us. This is Valeri and Luca, and we found the spot. And that's when the work began in earnest. We're not wearing camouflage. We're actually wearing mosquito netting, which happens to come in camouflage gear. Camouflage-colored gear. We're not trying to hide from anything, so far as I know. Well, it would be nice if we could have fooled the mosquitoes, but nothing helped. You know, a few seconds is about as long as you could stand without having that gear on you of some kind. It was really pretty awful. That part was definitely awful. So then the work begins in earnest. First of all, a team, most of it will, begins digging for this clay up and down the stream, different areas. We dug out about 1.5 tons of this clay. Part of the team, next part of the operation, I'll show that in a moment, involves panning. So that means you get a lot of clay, but you don't want the clay. You want the residue, which might have quasicrystal and meteorites and metals in it. Part of the team is simply going out hiking every day. Well, hiking, you know, mapping the structural geology of the area. And some of the team is in camp and analyzing materials. And so it's a multi-part organization of this team. The clay is this very thick, I don't know how to describe it, extremely thick, extremely dense, and has a kind of gluey consistency to it. So the first thing that happened was that the 3 shovels we broke. Sorry. The first thing that happened is the 3 shovels we brought for it broke. So nothing could be done by shovel. It was all done by hand and hand trowel, and mostly by will. So that was a pretty ugly job, but
What did you know to look for?
you don't know what to look for. You're just panning like crazy. You're gathering as much material as you can there, and you're not going to be able to analyze it till you get back. So yeah, so you have to be really fanatical and the panning part, because you can't bring back that much 1.5 tons of material. The panning part involves this kind of process. It's just like gold panning or platinum panning. You begin with this big pot of material, and you can see what he's doing. He's kind of dipping it in the stream, and he washes it around. And the idea is to take all the lighter material, the clay material, and clay it out and pan it out. And then you continue. Once you've finished up the pan, you've gotten to this much material that goes into this container, and then you repeat the process again. And here he is. He's panned out most of the material. Then it goes into yet another container, a little pot that's a porcelain pot that's about this big. I think that's what he's about to do. Is he's about to pour in the bottom, put it into this porcelain pot that goes into there. And that's not even the last stage. It then goes into yet a smaller little metal thing. You do one more round of panning, and then you boil it to get rid of the moisture. And then you get, so out of a pot of material that's about 20 kilograms, you end up with a little powder of material, useful material that way. And that's the material you're going to bring back with you and analyze. Some of it we could look at in lab and look for a couple of things, but you don't have the right equipment in lab to do this job. So here's an example. You know, when you got to the wood panning stage, and we're still far from done, here's the amount of material you have left. And you might notice there's a little shiny grain in there. That is gold. So we did find gold, and then they're hills. Getting out wasn't trivial. There were various adventures along the way. Again, I'm suppressing a lot of this story, but just to give you some idea, this is us looking back at the mountains we just came from just as we get back on the tundra again, and you see they're all white. So winter had struck. This was August 5th. Winter had struck the day we left the Korayaks, and we got out just in time. After that, well, not only could we not do any more work, could we not have done any more work, but it could have been harder getting out.
Excuse me, what was the latitude?
64. Yeah. So you're not quite. You're still south of the Arctic Circle, but you're pretty far out there, up there. Yeah. And it really didn't get dark at night, and it was actually there was a lot of wonderful scenes up there. So let me just close. I can't give you all the results. We've been working like crazy in the lab the last few months on the materials we got from there. But let me just close with just giving you just a few preliminary results, which I can tell you, and then be looking for results in the coming months. So first of all, just as I said, when coming back, you have to realize we had no idea if we had anything. You just have a bunch of grains of material, 60 bags of grains of material. Who knows what you've got? I remember taking a bet in the hotel the night before we left. What were the chances of finding even one other piece of meteorite in this? And you can ask yourself that question. What number would you have guessed? I think I guessed 0.01%. And I think the numbers went up to 1%. So even though we had worked hard, we really didn't expect to find something. After all, if you find even one piece of meteorite, there's nothing to say that you find any other piece of meteorite anywhere around there. That said, we did find another piece of meteorite. In fact, we found 7 grains since then out of that 1.5 tons. And this is an example of them. Although it looks huge in this picture, it's again millimeter size, a few millimeters in size. This is definite. I mean, a meteorite expert immediately recognizes this as sort of being classic meteoritic material. You can also then go back and show that properly chemically. And then you can kind of see there's kind of a shiny surface there. And if you take the diffraction pattern of that, there it is. It's a quasicrystal. It's an X-ray diffraction pattern. It's a 10-fold symmetry. This is quasicrystal. Chemically, it's the same as what we had before. Despite the complex story that led us to the Korayaks in the first place, which you might have had some reasonable reasons to be suspicious about, finding this with our own 2 hands, means that all that story was somehow correct. The crazy story was absolutely correct. That's really where the material came from. And there's more of it there to be found. And I'll just close with this image. So this is from a different grain. This is a slice through it. And you can see how there's kind of this knot of material in this sort of this fine matrix. Okay? So if you were to show this to a meteorite expert, this would have an instant recognition of what's called a carbonaceous chondrite. one of these meteorites formed from the very beginning of the solar system. Absolutely characteristic, this pattern. In fact, I've had that experience, just flashing it up, and that fraction of the audience goes, oh. Okay, but there's something unusual about it, which is there's grains like this and this one there, and those turn out to be metallic copper aluminum phases. Okay, the stuff that's supposed to have been impossible. So you see it was actually there in the middle of the chondrite, which means this we know formed in the beginning of the solar system. So now we're much more confident that this formed at the beginning of the solar system. That plus other evidence, which I haven't prepared here, is enough to, I think is letting us now piece together a story of providing us more and more details of how this material might have found. There's still a mystery how you would manage to make such a thing, but whatever it is, that mystery is telling us something about processes that occurred at the formation of the solar nebula or shortly after that we didn't know existed before. So that's going to be a byproduct of this search for natural quasicrystals in terms of this material. Of course, the search doesn't have to finish there, and at least as far as I'm concerned, will not finish there. We found this material. This is an interesting story in its own right, but the search can go on from there to look for others. So I'll stop there.